So what we've seen so far are the so-called direct comparison tests. So we compare directly the terms of one series with the terms of another series. There is another kind of test which, even though may look from the statement that they're a little bit more complicated because, as the name implies and suggests, they involve limits, but in fact it turns out that quite often they are going to be easier to implement because, as you're going to see in a minute, they do not require our checking any inequalities, and as you know, inequalities are often difficult to check. The direct comparison tests, they all require in the assumptions that we have some kind of inequality to prove. These two limits I'm going to show you now don't. So what do these two tests say? Well, the first one says that if the sum of the bn's is convergent, and if eventually the limit as n goes to infinity of an over bn is some finite number, as long as that number is not infinite, but it exists, so the limit exists and is a finite number, then the sum of the an's is also going to be convergent. Now, this is not as clear as the direct comparison test, is it? It involves a limit. Is not as intuitive and as obvious why this should work. But in fact, the proof works pretty much the same way. I'm not going to show you the technical details, but they're very much the same as for the direct comparison test. All we have to do is show that under these conditions, then the sum of the an's ends up being monotonically increasing. Well, that's clear, but it ends up being also bounded, and because of that, that turns out to be to provide convergence. So the idea is still the same as before. It's just that in the actual checking of the proof, we need to check a few more details to make sure that we convincingly prove that the sequence is actually bounded. Notice that the only case which is left out in here is the case where that limit is actually infinite. Well, we might say that limit doesn't exist in that case. That's true. But if it is infinite, well, of course, what that means is that the an's will end up being much, much bigger than the bn's, and so the fact that the bn's are convergent tell us absolutely nothing about what the an's do. Now, the other limit comparison test looks at the other kind of situation. So let's say that the sum of the bn's is divergent, and of course, because we're talking about positive sequences, it will have to be divergent to infinity. And also, let's assume that eventually that same limit that we saw before is some number greater than 0 or even infinity. Okay, so we are fine. Then under these conditions, then the sum of the an's is also divergent. And even here, the situation is still the same. As long as that limit is some number which is not 0, so some positive number or infinity, what that means is that the an is growing fast enough, maybe not as fast as bn, but is growing fast enough that it too will go to infinity. So in this case, again, it's same idea of the proof as for the direct comparison test, just a few more details to check to make sure that we can prove that the an's are large enough that they will eventually go to infinity. Notice once again that the only case which is left out is when that limit is actually equal to 0, because that means in that situation that the an's eventually are going to be much smaller than the corresponding bn's. If the limit of that ratio is going to become 0, that means that the an is going to become infinitesimally smaller than the bn's, which may actually lead it to lead them to add up to some finite number. Okay. So again, look at these two statements. Not as intuitively clear as the direct comparison test, but as we're going to see in class through examples, computationally sometimes more efficient. And make sure that you don't confuse the two situations. Remember, in order to get convergence, you don't want that limit to be infinite. If you're trying to prove divergence, you don't want that limit to be 0. So I said that these tests can be used and look quite simple and intuitively clear, but in the implementation sometimes there are some difficulties. So how are we actually going to use these tests? Well, we have to use it smartly. We can't just pick any series and or given a series. Once we're given a series, we cannot simply pick any other series whose behavior we know and try to compare it. We have to do it a little bit smartly. So how are we going to do it? So to perform these tests efficiently, what we're going to do is we're going to compare the given series to another series, okay? But we have to pick this series in a very smart way. Namely, first of all, we want to pick a series, of course, whose convergence or divergence is known. So we may want to pick a geometric series or a p-series or any other series whose convergence we have already established. And then that's not enough. What we want to do is we want to do that by eliminating from the given series pieces of lower power, as in the law of the jungle, as we did for limits at the beginning, when we're trying to compute limits of ratios and so on. Remember, we are computing the limit of a ratio. So what we want to do is we want to compare our series to something else which has pretty much the same structure, less the fluff. So what we're trying to do is get rid of all the things of lesser powers, things that when we go to infinity are really not going to be very important, and then hope that the test will work under those conditions. Now, there is no guarantee that our first choice will work. So if that fails, what you want to do is try a different kind of series to compare it to, based on the first experience, but also based on whatever other experience you have accumulated. So surprise, surprise, I'm going to encourage you once again to do a lot of practice, because all that practice is going to allow you to be very familiar with the behavior of certain series, as well as very familiar with what happens when you compare one kind of series to another. However, when all is said and done, these tests do not always work. So you may want to be prepared to abandon them and use a different procedure if these tests are not going to use. And yes, don't worry, we will be seeing some other tests. So in case these ones don't work, it's not the end of the world. But if these ones work, and once you learn how to apply this technique together with the tests themselves, they can be very effective, very efficient, very powerful, and very useful in all kinds of situations.